Hello class. Topic 22 is solving ODEs with using Laplace transforms. Now this is where we use the information that we learned from topics 19, 20, and 21 and combine that information and actually solve ODEs from start to finish. We will only do 3 tasks in this lecture. First task, solve the ODE with initial condition using the Laplace transform. Y prime plus 3y is equal to t squared, and y of 0 is equal to negative 4. We'll begin by doing a Laplace transform of each side. So the symbol for doing that is just putting this curly L in front of each side, and then I can use the property of Laplace transforms regarding doing a Laplace transform of a sum by doing just a Laplace transform of the 2 pieces separately, and then I can factor the 3 in front of the Laplace transform of the second component. So this really just winds up becoming the Laplace transform of y prime plus 3 times the Laplace transform of just y, and then equals, and we have to do the Laplace transform of the other side as well. Now I'm going to refer to our notes from topic 22 and to help me doing a Laplace transform of the derivative. Eventually it would be nice if you got to the point where you had this memorized, but we can look this up if necessary. So going back to topic 22 and focusing in on this part right here, to do the Laplace transform of a derivative, we get s times the Laplace transform of the function, the original function f, the non-derivative, and then minus little f of 0. So what that looks like in the context of our current problem, we're using y instead of f, but the Laplace transform of y prime will be s times the Laplace transform of just y, which we're going to use as capital Y for that. So this is y, and it's a function of s. This stands for the Laplace transform of little y. I'll leave the of s part off and just say capital Y. And then minus little y of 0. And this is the result of doing the Laplace transform of y prime. And then we have plus 3 times, and the Laplace transform of little y is just capital Y, so I'll go back to capital Y for that, equals, and now we want to do the Laplace transform of t squared. So let's go back to our table from topic 20, and we have a t squared function, and we want to do the Laplace transform of that. So the n is a 2, so we're going to have a 2 factorial over s to the 2 plus 1. So just change both those n's to 2's. So we have 2 factorial, which is 2, over s to the 2 plus 1, so over s cubed. Okay, now what we're going to do is we're going to use our initial condition, the fact that y of 0 equals negative 4, to replace this here with negative 4. So we can just do that really quick. S times y minus negative 4, so this will become plus 4, plus 3 capital Y is equal to 2 over s cubed. And now we're going to isolate the capital Y. So subtracting 4 will be in order. Grouping, and then I'm going to group these two capital Y terms together and factor out the capital Y. So we have capital Y times s plus 3 is equal to 2 over s cubed and minus 4. And then finally, divide. So we get capital Y is equal to 2 over s cubed times s plus 3 minus 4 over, and I'll just divide each term by its own s plus 3. And now I want to start thinking about how to do a reverse Laplace transform, because we have y, capital Y, which is the Laplace transform of y, is given by this function of s. And if we can figure out how to do the inverse Laplace transform, we can get what little y, which is what the solution to the differential equation is. Now this part here is we can already figure out how to reverse that Laplace transform using our table backwards. But this first fraction here needs to be decomposed first. So we have to do a partial fraction decomposition. So I'm going to do that work over here on the side. So I'll begin by writing down 2 over s cubed times s plus 3. So this is what needs to be decomposed. The first rule is that I see that there are, in fact, a total of 4 factors here, right? There's s, 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 and s plus 3. So I'm going to decompose into 4 fractions. There we go. There's our 4 fractions. And each denominator gets its own factor. So we have the s's are in each denominator, and then the s plus 3 gets its own denominator. Now the second rule of decomposition says that the constants go above lines, and lines go above prime quadratics. Now all of these denominators are linear, so we have to put constants above all of them. So just capital A, capital B, capital C, and capital D. And then the third rule of decomposition is that if you have any repeated denominators, increase the power as you go. So we have s has been repeated a total of 3 times. So the second time we write s, we should put s squared, and the third time we write it, we should put s cubed. And here's our setup for the decomposition. Now we're going to do is multiply both sides by the denominator, which is s squared, or s cubed rather, times s plus 3. And then we're going to distribute this to each of these fractions and on both sides of the equation, and do the simplification as we go. So on the left side of the equation, the denominator will cancel entirely, leaving just 2. Next to the a, one s will cancel, but we'll have an a times an s squared, and then times an s plus 3. Next to the b, one s will cancel, or sorry, s squares will cancel, leaving just a single s, so b and s, and then s plus 3. Next to the c, all the s's will cancel, but the s plus 3 will remain. And next to the d, the s plus 3's will cancel, so we'll have d times s cubed. Now from here, if you recall, there are a variety of tactics for determining what a, b, and c are. Method 1 is where we replace s with different choices so that a lot of the unknowns will cancel. So I'm going to use method 1 as much as I can here. For example, if I choose s is equal to 0, this is going to be a convenient choice because 3 of the 4 unknowns are going to cancel. And changing s to 0 leaves a 2 on the left side because there's no s's over there. This a term will cancel out, this b term will cancel out, the d term will cancel out, but only we'll get a 3c here, and that's it. So we get a bunch of zeros and then a 3c. So this tells me right away what c is. C has to be 2/3. Now another choice of s that is going to be convenient is to choose -3. And choosing s equals -3, again, doesn't change the left side of the equation. That's still just 2. But plugging in -3 is going to zero out a, b, and c. So we're just going to get this term over here. And when s is -3, that's going to be -27d. So this gives us that d is -2/27. Now there are no other choices of s that will cancel some of these unknowns. You could choose other s's though. You can continue with method 1 if you will. Let s be 1, let s be 2, and then create these equations that have a, b, c, and d. And then since we know c and d, we could just narrow that down to an equation that only has a and b, and then solve that system. Or I'm going to use method 2 actually to finish out by equating coefficients from both sides. So I'm going to expand this, and I'm not going to do it entirely. I'm only going to expand as much as necessary to deduce what I need to deduce to find out what a and b are. For example, gather all of the s cubed terms. Now when I multiply these out, I'm going to see an as cubed. This will have no s cubes, this will have no s cubes, and here I have a ds cubed. So there's only 2 s cubed terms. And when I factor the s cubed out, it'll be a plus d s cubed. These would be the only s cubed terms. Now let's shift to the s squared terms. Now there's going to be an as squared times 3, so there's going to be 3as squared. There's a bs squared, and that's going to be the only s squared terms out of all this. So we're going to have a 3a plus a b s squared. Now I could continue expanding and regrouping, but I see that I don't need to because this will be enough information for me to find both a and b. Now, on the other side of the equation, notice over here there are no s cubes or s squares. Right? So you could imagine that there's a 0 s cubed over here. So you want to equate coefficients. So a plus d has to be 0. So, and also there's no s squared, so both of these coefficients have to be 0. So that's going to create 2 more equations. A plus d has to be 0, and 3a plus b has to be 0. Okay. Let me write that over here instead. Now, we can finish out and figure out what a and b are because I know what c and d are. So this first equation will allow me to find a. We know that d is negative 2/27. So we know that a has to be the opposite of d. So in other words, a has to be positive 2/27. And over here, we know that b has to be equal to negative 3a. Therefore, b has to be, and since I just figured out what a is, multiply that by negative 3, we get negative 6/27, which simplifies to negative 2/9. And this gave me the last two unknowns. Okay, next, we're going to go back to what our y expression is. Let's go back over here. And following our decomposition, we have a is over s, and a is 2/27. All right, so I'm just going to effectively rewrite this composition over here with the correct a, b, c, and d, and that'll decompose this first part. So we have a over s, so 2/27 over s, and I'm going to put that 2/27 just in the front instead, and think of this as, there's my a over s essentially. We just do a times 1 over s, plus b, right, looking at this next one, plus b over s squared, and b is negative 2/9, so we're going to have minus 2/9 times 1 over s squared. That'll be satisfactory. Plus c over s cubed, and c is 2/3, so plus 2/3 times 1 over s cubed. And then finally plus d over s plus 3. And d is negative 2/27, so minus 2/27 and 1 over s plus 3. So that's the result of just decomposing this first part. But don't forget, we also have this minus 4 over s plus 3. And notice we have some similar terms here. Let me write that a little bit better there. These last two are similar and can be combined. So here's how I'm going to do that. I'm going to think of this 4 as a coefficient instead, and to get a common denominator, 4 is multiply top and bottom by 27. 4 times 27 is 108. So this is the same thing as just doing 1 minus 108/27. Now I'm going to be able to combine these together. They have, just by combining the coefficients, it's going to be minus 110/27. So we'll do that part next. So let me just copy this, because the rest of it won't really be different. And combine these to negative 110/27. Get rid of this term, and here we go. So here's our capital Y function, and now we need to do reverse Laplace transforms. So again, referring back to our table from topic 20, if ever you have a k over s, or k times 1 over s, and you want to reverse that, it just goes back to a constant k. We do the inverse Laplace transform, takes me back to just that constant k. So we have the first one, 27 times 1 over s. The reverse Laplace transform of that, so we'll go back to y, little y now. It's just going to be the constant k. In this case, the constant k is 2/27. Okay, the next one. The next one is a constant times 1 over s squared. So looking back at our table, we want to shift gears down to this one because we have s to a power. And if we want this to be s squared down here, then n has to be 1, which means we need a 1 factorial up here. So in other words, just a 1. So if we have a 1 over s squared, that would be the Laplace transform of t to the 1, or just t. And of course, if there's a constant in front, we just keep the constant in front. So the inverse Laplace transform of this second piece is going to be minus 2/9 times just t. because the inverse Laplace transform of 1 over s squared is t. Okay, the next one, we have a 1 over s cubed. So let's go back to our table. Now, if you want this to be s cubed down here, then this n would be a 2. So you would need a 2 factorial up top. So we need to have, which is just 2. So we need to have a 2 over s cubed. And if this was 2 over s cubed, the inverse Laplace transform would be t squared. Okay, well, currently I don't have a 2 over s cubed, but I can do this. I can borrow the 2 that's right next to it, or I can change that to a 2 and counter it with a 2 over here, do that kind of trick. Or I could just, as I said, I'm going to move this 2 over, make that a 1/3 and put the 2 right there. Now the inverse Laplace transform of 2 over s cubed is t squared. So when I do the inverse Laplace transform of this term, I get 1/3 of t squared. So plus 1/3 of t squared. And then finally we have our last term right here, a 1 over s plus 3. Let's see, with a constant in front, but let's see what we can do with this 1 over s plus 3, looking back at our table. And it looks like the entry to focus on is going to be right here, 1 over s plus 3. So we just need a to be a negative 3. So the inverse Laplace transform of 1 over s plus 3 will be e to the negative 3t. So we're going to get minus 1/10/27, that constant will stay, and then the inverse Laplace transform of 1 over s plus 3 is e to the negative 3t. And there it is. There is our solution to the differential equation. I leave it to you to verify that, in fact, this is a solution, meaning that if you verify the initial condition, plug in 0 for t, you should get negative 4 out of all of this. And if you also do the derivative of this function and then plus 3 times that function, it should all just boil down to t squared. So I'll leave it to you to verify that this is in fact the solution that we are after. Let's go to the next one. This time we're doing a second degree, and the third one will also be a second degree. So we'll do a couple second degrees in our lecture notes. Solve the ODE with initial conditions using the Laplace transform. Again, I'm going to do a Laplace transform of each side to begin. And I could distribute the Laplace transform across here. So we're going to have a Laplace transform of y double prime minus 9 times a Laplace transform of just y equals, and then we'll have to do a Laplace transform of the other side, which is 2 times sine 2t. Okay, the Laplace transform of the second derivative. Let's go back to our table here and go over to the second column. Here's a Laplace transform for the second derivative, and if ever you need to use Laplace transforms on a third order differential equation, you could use this last entry, but let's focus on right here. We're going to get second, or s squared times the Laplace transform of the function minus s times little f of 0 minus f prime of 0, little f prime of 0. So we're going to adapt this and use it, but in terms of y. We're using y instead of f. So we have the second derivative. It's going to give us s squared times the Laplace transform of y. So s squared, capital Y, minus s times little y of 0, and then minus y prime of 0. And that is the Laplace transform of a second derivative. Now we're going to do this next part here, minus 9 times the Laplace transform of y. So that's just minus 9 times capital Y. And then the right side of this expression, we need to do the Laplace transform of 2 sine 2t. Okay, well this 2 is just going to stay, so we just got to do the Laplace transform of sine 2t. Let's go back to our table and focus on this part of the table. The Laplace transform of sine of 2t will be 2 over s squared plus 2 squared. So it'll be 2 over s squared plus 4. And since there was a 2 here in front, we're going to multiply that by 2 as well. So we're ultimately going to get 4 over s squared plus 4 is our Laplace transform of 2 sine 2t. Okay, from here now we use the initial conditions, and also we are going to isolate the capital Y. So there's two initial conditions right here, so we're going to replace those with these numbers, and then I'm also going to move those to the other side of the equation. So let's see how much of this we can just kind of do all at once. So first I'm going to keep the y terms on the left side of the equation and factor out the capital Y. So we have y times, capital Y that is, times s squared minus 9. This y of 0 is going to be 3, right, given the initial condition. So we're going to have minus 3s, but I move that to the other side of the equation. So we have, over there already, we have 4 over s squared plus 4, and then we're going to be adding 3s to each side of the equation. Then y prime of 0, this here is a 1. Y prime of 0 is a 1, so this is a minus 1, but I'm going to add that to the other side, so we have a plus 1 on the other side. Okay, hopefully that wasn't too much done in one step. And finally, we're going to divide everything now by s squared minus 9. Now there's a couple of schools of thought here. Let me go back up to this last example. In this last example, I did a partial fraction decomposition of just this, and because I didn't sense a need to do a partial fraction well, you couldn't do a partial fraction decomposition on that last term. Now what you could have done instead here is you could have combined these together first by getting a common denominator and then doing a partial fraction decomposition of the entire thing. That's the strategy I'm going to use here. So before I divide both sides by this s squared minus 9, I'm going to get a common denominator over here on this side. So I'm going to multiply this here by s squared plus 4 over itself to get a common denominator so I can combine those together into one fraction. Okay, so this leads me now to the following statement. Y times s squared minus 9 is equal to, and we have a common denominator. I'm going to go ahead and FOIL these together. So we have 3s cubed. I'll write that first. 3s cubed. Then we're going to have a positive s squared is going to happen, so plus s squared. Then there's going to be a positive 12s. Then a positive 4. But we already have a 4 over here as well, so those will combine to be a positive 8. So I think I expanded this correctly, and all of this is over now the common s squared plus 4. And then, of course, the final step is now to divide both sides by s squared minus 9, which is a difference of squares and it factors. Let me just copy this. I'm going to shift that over slightly. Now, s squared plus 4 is a prime quadratic. It does not factor over the real numbers, so we leave that part. But this s squared minus 9 that I'm going to divide down to this space here, I will factor it as well. It's s minus 3 times s plus 3. So the advantage of getting a common denominator over here first was that now capital Y is expressed as a single fraction that we just need to do one decomposition. Whereas in the last example, we had to do a decomposition, and then remember this piece was involved as well, and then I had to combine those two pieces here to get this final piece. If I had combined these together first and then divided by s plus 3 and then did a single decomposition, I would have been taken straight to this line right here. So just a variety of ways of doing this. Okay, now let's set up the decomposition. So I'm going to grab this part here. I'm going to pull it off to the side. Let's do that work over up here. And let's get the decomposition set up. Let's start with the linear factors first, the simple factors. So we're going to have a constant over the linear factor s minus 3, plus a constant over the linear factor s plus 3, and then plus a arbitrary line, so a cs plus d, over the prime quadratic s squared plus 4. And rule 3 of decompositions don't apply because there are no repeated denominators. Now I'm going to multiply both sides by the original denominator, so by this. Let's go ahead and put that right here. Make that pink as well, okay. And then distribute across there and simplify. Let me move all this over just slightly. And simplify the fractions as I distribute. Okay, so on the left side, we're just going to get this numerator. So this is just going to be all that's left. Equals. Now next to the a, we're going to get the s minus 3's to cancel. So next to the a will be an s plus 3 and the s squared plus 4. Next to the b, the s plus 3's will cancel, leaving s minus 3, and then also the s squared plus 4. And then, let me move this over slightly, give myself space. And then for the third and final fraction here on the right side of the equation, the s squares plus 4 will cancel, giving us a cs plus d, and put it in its own parentheses. And then we have the s minus 3 and the s plus 3. Again, give myself a little more space. Okay, I think I can get away with using primarily method 1 the entire time here. Let's make sure this work here stays separate. Let me do this. Okay, and for example, if I let s be 3, let's start with that one. Plug in 3 on the left side of the equation. We're going to have to do 3 cubed is 27 times 3 is 81, plus 9 is 90, plus 36 is 126, and then plus 8, we get 134. So we get 134 on the left side of the equation when I plug in s equals 3. And s equals 3 is going to cancel these terms over here, leaving just the a term. So that's going to give me 3 plus 3 is 6, and then 3 squared plus 9 is 13, and 6 times 13 is 78. So we get 78a. This tells me that a is 134 over 78, which reduces to 67 over 39. Okay, let's now use s equals negative 3. Plugging in negative 3, this will be negative 81 plus 9. That takes us down to negative 72. Yes, negative 72 plus 8, negative 64, but then minus 36. So that takes us to negative 100. And plugging in negative 3 is going to zero out, it's going to zero out the a term, that's going to go away, and zero out the c's and the d's. Those will all go away. So just this term here will be left. And plugging in negative 3 squared plus 9, that's 13 times negative 6. So we get negative 78a this time. And not a, but b, negative 78b. And solving for b, we get b is positive 100 over 78, but 100 over 78 is the same thing as 50 over 39. So 50/39 is b. Now let's plug in 0. 0 is going to be a nice choice to cancel a few things here. We get a clean 8 on the left side. That part was easy. And plugging in 0 for s, we get 12a here. Plugging in 0 for s, we're going to get plus 12b. Sorry, minus. Plug in 0, this will be a minus 3 times a positive 4. So it's going to be minus 3b. Almost made a mistake. So minus 12b. Almost made 2 mistakes. And then plug in 0 for s over here. That's going to cancel the c. Leave the d. This is going to be a negative 9 right here times this d. So net minus 9d. Now, we know what a and b are. So we get to replace a and b with these fractions. And to save time, I went ahead and actually calculated what d is going to be. But you can plug in a and b right here, and then solve for this d, and you will get d is negative 4/13. So I'm going to leave the work to save time, but this is what you should get. I do recommend you try to confirm this, but you should get d equals negative 4/13. And now there's no other choice of s that's going to cancel an unknown, but since I know 3 out of the 4 unknowns, I can let s be anything. So I'm going to finish this problem entirely using the first method for finding these unknowns and not by equating coefficients, although that could be very useful too. If you, let's see, what's the only unknown we don't know is c. Okay, so if I plug in s equals 1, on the left side of the equation, I'm going to get 30 or 24. So I get 4 plus 8 is 12 plus another 12. Yeah, 24 on the left side of the equation when s is 1. When s is 1, we're going to get 4 times 5, so we get 20a. Plug in a 1, we get into the next part right here, and we get negative 2 times 5, negative 10, so negative minus 10b. And plug in 1s for all the s's over here. This will be negative 2 times 4, so that's going to be negative 8. This will just be c plus d. So it's going to be, and distribute the negative 8, so it's going to be minus 8c minus 8d. And because I know what a, b, and d are, I can find c. And again, I'm going to skip ahead. I've already done this ahead of time, so I know what the c is. The c should wind up being 0, actually, in this case. And I'll let you confirm that. So there's our partial fraction decomposition finished, and we know what the a, b, c, and d are. So I'm going to go back to our y expression here and replace it with its decomposition. So capital Y function is equal to, now the a was over the s minus 3. So the a was 67/39. That was over the s minus 3. The b was over s plus 3. And the b was positive 50/39. So 50/39 times 1 over s plus 3. And then we had a cs plus d over s squared plus 4. But c is 0, so we really just have to do the d over s squared plus 4. And d was negative 4/13. So we can just write this as minus 4/13 times 1 over s squared plus 4. Okay, now we are prepared to do reverse Laplace transforms of these three pieces. The reverse Laplace transform of 1 over s minus 3 is e to the 3t. I'll leave that to you to confirm with the table. And the inverse Laplace transform of 1 over s plus 3 is e to the negative 3t. So we get little y, finally, of t. This is a function of t now, our solution to the differential equation. We have 67/39 times e to the 3t, is the first one, plus 50/39 e to the negative 3t. And for this next one, to do the reverse Laplace transform of 1 over s squared plus 4, let's go ahead and look at our table for that. That's going to be related to our sign here. We have s squared plus 4 down here, so b is 2. So I need a 2 up here before I can do the reverse Laplace transform. So we have, I'm going to break apart this 4 right here into 2 times 2 because I want to put a 2 up above there. So now we have a 2 over s squared plus 4, and the inverse Laplace transform of that is sine 2t. So we have minus 2/13 sine 2t. And this is our solution. Again, I leave it to you to verify that it meets the initial conditions as well as that it satisfies the differential equation. And one last one, another second order ordinary differential equation. Let's begin again by Laplace transform both sides. And I'm going to go ahead and do some skipping of the steps. I won't write all the curly L's. Let's just do the Laplace transform of y double prime. It's going to be s squared times capital Y minus s times little y of 0, and then minus little y prime of 0. That's the Laplace transform of just the y double prime. Okay, next we do plus 4 times the Laplace transform of y prime. So we have plus 4, and then I'll use some parentheses. The Laplace transform of y prime is s times capital Y minus little y of 0. And that all needs to be multiplied by the 4, so I'll put that in parentheses. And then plus 3 times the Laplace transform of y, so plus 3 times just capital Y, equals, and now we need to do the Laplace transform of t times e to the 2t. Let's see what our table can do to help us with that. Down here is a good place to begin. Also, you can also use this idea here that if you do e to the at times a Laplace, or times a function f, then you simply, to do the Laplace transform of this, you do the Laplace transform of little f by itself, but then you evaluate it at s minus a instead. That's what this is saying to do. So in this case here, we have e to the 2t times t. So the little f of t is just t. So you look over here and say, what's the Laplace transform of just t? So you look here with n being 1. So you get 1 over s squared. So 1 over s squared is the Laplace transform of t. So if you're going to do the Laplace transform of t times e to the at, then you're going to get the Laplace transform of just t, but evaluated at s minus a. So if the Laplace transform of t is 1 over s squared, we just simply evaluate that at s minus a. So it'd be 1 over s minus a squared. Or you can, all that's summarized by this entry right here as well. So if you have t to the 1 times e to the, we have e to the 2t, then the n is a 1 and the a is a 2. So this would be 1 factorial, this would be a power 2, and this would be an s minus 2 inside there. Okay, all of that leads to the Laplace transform of t times e to the 2t is going to be 1 over s minus 2 squared. Okay, there's our setup. Now we get to use the initial conditions and replace some numbers here. I'm going to take the time to rewrite this and distribute the 4 so it's not too cluttered. But we have, I'm trying to avoid doing too many steps at once. So you have s squared times capital Y minus s times y of 0. So we have minus 2s minus y prime of 0. So it's going to be plus a 1 there. And then we have plus a 4sy. Distribute the 4, and then distribute the 4 here as well. So we have 4 times negative y of 0. Y of 0 is 2, so that's negative 8 essentially. So we get when I distribute that. And then we have plus 3 capital Y is equal to 1 over s minus 2 squared. Okay, and I'm going to, these 3 terms here can all be combined / moved over to the right side of the equation, and then all the terms that still have an s involved, which there's 3 of them, can stay on this side of the equation with the capital Y factored out. So that winds up being s squared plus 4s plus 3 times capital Y is equal to 1 over s minus 2 squared, and there are other terms I'm going to move over, so plus 2s. These together make negative 7, so then just add 7. So 2s plus 7. I'm going to go ahead and get a common denominator for this again. And I'm not going to expand the numerator this time. I do notice that this here, this also factors, which is convenient. That's just going to be s plus 3 times s plus 1. And after I get a common denominator on the other side, I have a 2s plus 7 that needs to be multiplied by its own s minus 2 squared, so that everything is over an s minus 2 squared. And this time, I'm not going to bother expanding this. You're going to see that we really don't need to expand it to complete our task. And the final step, of course, is now to divide these 2 terms down to the other side to get capital Y isolated. So let's just copy this. Move this over a little bit and join that denominator with an s plus 3 and an s plus 1. All right, so here is the fraction that we want to do a decomposition of. copy that, paste it up here, and let's set up the decomposition. Let's do the simple denominators first. There at the s plus 1 is going to get an a above it. The s plus 3 will get a constant b above it. And the s minus 2 is a repeated denominator, so it gets, you get two more fractions out of this, where the s minus 2 is repeated, s minus 2, s minus 2. And since they're both linear, you get two constants above those. But the third rule of setting up a decomposition says that with the repeated denominator, increase that power. So here's our decomposition. Now I'm going to multiply both sides by I won't write it, but I'm going to multiply both sides by this denominator, and then simplify. So on the left, let's see how much space I'm going to need here. Let me move this up slightly. On the left side of this equation, we're going to get just this numerator. Okay, equals a times, and what will be left next to the a, the s plus 1s will cancel, so the s plus 3 will still be there, and both s minus 2s will be there. Next to the b, the s plus 3s will cancel, so the s plus 1 will still be there, and both s minus 2s will be there. Next to the c, the s plus 1 and the s plus 3 will both remain, but one s minus 2 will cancel, leaving the other s minus 2. And then finally, next to the d, the s plus 1 and s plus 3 will still be around, but the s minus 2s will both cancel. So there's the result you get after distributing that denominator. And let's see what we can do with method 1 only. There's some obvious choices of s that are going to be convenient. For example, if s is 2, let's start with that one. So you get to plug 2 into all of this. Well, this is convenient that that's going to zero out, meaning that's all gone. So you just get a 1 on the left side of the equation. And on the right side, let's see, s equals 2 is going to cancel the a term, cancel the b term, and cancel the c term, but we will have this d term. Let's change the s's to 2's, and we get a 3 times 5, so we have 15d. So this gives me d right away. That d is 1/15. S equals -3 seems to be a next good choice, or -1. Let's do -1 first. No particular reason, but plug in -1. -1 plugs in for both of these s's, so we're going to get 5 right here and 9 right there. So this is going to be 45 plus 1, we get a 46 on the left side of the equation. -1 is going to cancel the b, c, and d. These terms are all gone when I plug in -1, but this term is still here. So we get a 2 times 9, 18a, if I did that right. And this allows me to solve for a. We get 46/19, which is 23/9. 46/18 is 23/9. Okay, now let's do s equals -3. Let's see what magic happens. Plug in -3 over here. That's going to be a 1 right there. That's convenient. And -3 minus 2, -5 squared is 25, plus 1, so we get a 26 on the left side of the equation. -3 is going to cancel the a, c, and d. Those three are all gone, so we only have the b term. Plug in -3 plus, that's going to be a -2 right here. This is going to be a 25. So we get -50, so -50b. And we can divide. So we get b is therefore -13/25 after you reduce it. And these are the only choices of s that will cancel, but I have 3 out of the 4 unknown, so I can pick any choice of s now. 0 would be an easy one to choose. And let's see what equation emerges as a result. So we have 7 right there. This is a 4. 4 times 7 is 28 plus 1, so we get a 29 on the left side of the equation. Plug in 0. This will be 3 times 4, 12, so we have 12a. Plug in a 0 here next. We get 1 times 4, so we have 4b plus 4b. Plug in a 0 here next. We're going to get a 1 times a 3. That's a 3 times negative 2 is negative 6, so negative 6c. And then finally, plug in a 0 here. That's just going to be a 3 times d. Plus 3 times d. And since I know what a, b, and d are, I can ultimately solve for c. Now, this will be a little bit tedious because of all the different denominators, and I already did this ahead of time, but I suggest you take the time to confirm and see that you get c is equal to negative 8 2/25. Okay, so the decomposition is done. Let's keep that separate. Now I'm ready to finish out our problem. Let's go ahead and write the decomposition next to our y, our capital Y. So a was over s plus 1, and a is 23/9. So we have 23/9 over the s plus 1, so times 1 over s plus 1. And then plus b over s plus 3. B is negative 13/25, and that's over s plus 3. Right, times. And then c is over s minus 2. C was the negative 8 over 225 times a 1 over s minus 2. And then finally, the d is 1/15, and that is over, so plus 1/15, and that is over 1, or it's times 1 over s minus 2 squared. Okay, so here's our capital Y function. Now we want to be able to do the reverse Laplace transforms. Well, the inverse, this is a 1 over s minus a situation where a is negative 1. So our table suggests that the inverse Laplace transform of 1 over s plus 1 is e to the negative 1 times t, just e to the negative t. So let's go to little y now as our solution. We have 23/9 e to the negative t. This one here, the inverse Laplace transform of 1 over s plus 3 will be e to the negative 3t. So minus 13/25 e to the negative 3t. Inverse Laplace transform of 1 over s minus 2 is going to be e to the 2t. So we have minus 8 2/25 e to the 2t. And then finally, let's see what we can do with this one here. We want to do the inverse Laplace transform of 1 over s minus 2 squared. All right, let's look at our table. Looks like we're in this realm right here. So we can see that the s minus 2 suggests that the a is going to be 2, and we want this to be a squared, so n has to be a 1. So we need a 1 factorial up top, which we already have. So if this is 1 over s minus 2 squared, tells us that the inverse Laplace of that will be, n will be 1 and a will be 2. So this will be t times e to the 2t. So nothing needs to be adjusted. We already have the correct numerator up there. So the inverse Laplace transform of this is t e to the 2t. So we have plus 1/15 t e to the 2t. And there is our solution. All right, this wraps up how to use Laplace transforms to solve ODEs with initial conditions from start to finish, and using a partial fraction decomposition as a fundamental tool for accomplishing this task.